Okay, so I'm going to go through chapter 20 on abstractions. Now, we talked about abstractions all throughout the course. We talked about abstraction when we were learning about the internet and how the layers of the internet are an abstraction. We also talked about how number systems are an abstraction. And then when we started to program, when we learned how to make functions and procedures, we said that those were abstractions too. So we have seen them all throughout the course. So an abstraction has two roles in a program. It reduces the complexity and it helps you hide the details of a procedure inside of the procedure. So when you're reading the program, you can see that you're calling the function, and if you've named it appropriately, you should know what the function's going to do by its name. There are many layers to any abstraction, and when it comes to an abstraction, less is more. The less detail, the more abstract. So what do you need to know about an abstraction for the AP exam? Abstractions are defined in terms of level or layer. A high-level abstraction is more general. A lower level abstraction is more specific. Lower level abstractions can be combined to make higher level abstractions. And then it says, see Appendix D for a list of abstractions in terms of their level. So I wanted to show you this. So I'm going to minimize this just a little bit, and this is in your notes. So when we're looking at a computer, our high-level abstraction at the highest level would be the data storage, the hardware like the motherboard, and the software such as a block-based language. Those are the high-level abstractions. At the lowest level, we're talking about the most simplistic parts of the computer. So we're talking about binary digits, the transistors that make up the central processing unit, and the binary instructions that are part of the machine code that allow the processor to use those ones and zeros to actually make things happen. So back to the review. When designing a program, programmers use and generate many examples of abstraction to study, test, or create something that may eventually be real. Some of these include the fact that we may write a program to simulate a situation. So because we're simulating something, that makes it an abstraction. As we learn to be more advanced programmers, we're going to learn that we can make objects, and those objects, those software objects, can represent something from the real world. And then finally, we can write programs to test an idea or a theory, and if we provide the right input, it could make predictions and serve as a model in the future. So any program contains examples of abstractions. So like I mentioned, all digital data is an abstraction at the lowest level. All data eventually becomes binary digits that the computer interprets. The source of the bits could have any of the following. So hex, decimal, color codes, characters, operations, and programming commands. Bits are grouped to represent color by RGB numbers, red, green, and blue. So it would be in a mono red, green, and blue in hex, in binary, or in decimal. If you saw FFFFFF or 255, or all ones, that would be white. If everything was zero, it would be black. The use of abstraction tells you information about the layer you want to see. That's true for every symbol, language, and part of the computer. This is true no matter what you're trying to model or understand. Abstractions occur in hardware and software, and again, it's referring to Appendix D. A program created to solve or understand a problem is an abstraction of that problem. A program simulating a game is an abstraction of that game. A program that automates an important behavior in a program is an abstraction of that behavior. So in a program, if you had a function that calculated an average, then that function is an abstraction of that actual calculating of the average. Here's one that's very interesting, and this shows up on your rubric for your create task. A data structure, such as a list, models a collection of items that could be grouped together to simulate a real situation. For example, a list of playing cards simulates a deck of cards. Ultimately, this structure is stored as bits. A motherboard contains a CPU and memory. Within each of these are several details, such as chips or logic gates. And we saw that here. We saw hardware, the motherboard. We could see it all the details in between the high level and the low level, and finally down to the transistor level. Converting data often comes at a cost. So when we do convert data, sometimes the data cannot be converted without losing some information. So, for example, if I was doing a recipe and I needed a third of a cup, 1/3 cannot be stored on a computer. It has to be converted into a decimal number. To teach a computer in a language it understands, infinite math concepts are modeled by finite representations of infinity. So that's something we have to look out for. Some numbers need to be rounded to be stored. So if I have a number that has 5 million decimal places, that's unrealistic for us to store that number. So we're going to have to round the numbers. And this is called an overflow error. So in terms of number systems, you are responsible for decimal, binary, and hexadecimal number systems and going from one to another, and I will review that in a separate video. The hex number system is used to fit more data into less digits. So we learned that 4 bits represents one hex number. So if I have a 16-bit binary number, I could represent the same thing with 4 hex digits. Abstractions are useful in computer science. They provide a common language to describe parts of a computer like we see here. There are also a tool in programming and simulating reality, and through an abstraction such as a program, we can try out hypotheses with real-world consideration. Through our design decisions, we decide which details to keep or remove. Models and simulations are created on a computer to form and refine a hypothesis, like I mentioned. Time required to run a simulation depends on the following: the level of detail and quality of the model and the hardware and software being used. So what do you need to be able to do with an abstraction? You need to be able to identify and or use layers of abstraction to serve a purpose in a program. You also need to recognize examples of overflow errors. Here's an example of a fraction. You need to be able to convert to and from positive integer values stored in any of the following number systems: binary, hex, and decimal. Okay. Refer to Chapter 17 for practice with versions of abstractions related to the programming language used at the end of course exam. These include logic gates, robot movement, and related algorithms. Okay, so those are the highlights of abstraction, and you can